Imagine falling through an atmosphere thicker than soup, where the sky above you glows a murky, perpetual orange, and somewhere far below, hidden beneath layers of hydrocarbon haze, lies a surface harder than concrete, yet covered in lakes of liquid methane. The air presses against your hull with crushing density, not enough to destroy you, but enough to make every meter of descent a battle against forces that refuse to behave like anything we know on Earth. The temperature hovers at minus 179 degrees Celsius, cold enough to freeze nitrogen from the air itself, yet warm enough by this moon's standards to sustain an alien weather system where methane rains from toxic clouds and carves rivers through landscapes made of water ice as hard as granite. This is not science fiction. This is Titan, Saturn's largest moon, the only place beyond Earth where rain falls, rivers flow, and seas stretch across alien shores. And it is one of the most terrifying places in the solar system to land. In January 2005, the Huygens probe became the only human-made object to ever descend through Titan's atmosphere and touch its surface. For 2.5 hours, it fell through that thick, smothering haze, instruments struggling to pierce the gloom, sending back data so strange, so unexpected, that engineers are still unraveling its mysteries decades later. What Huygens revealed was not just a world, but a warning. Titan's thick atmosphere, the very feature that should make landing easier, transforms descent into a prolonged nightmare of heat, drag, and disorientation. Tonight, we will descend alongside that probe into alien hell. We will explore why Titan's dense atmosphere, 10 times thicker than Earth's, creates physics so punishing that engineers lose sleep over every calculation. Why a moon with parachute-friendly air might actually be more dangerous to land on than airless, vacuum-exposed worlds. Why the cold is not just cold, but a cryogenic assault that turns familiar materials brittle and strange. And why, despite all this terror, Titan remains the most scientifically tantalizing destination in our solar system, a place where the boundaries between hospitable and hostile blur into something we have never encountered before. If you are ready to understand why landing on Titan is worse than it sounds, far worse, then settle in. Let us begin our descent into the orange dark. In all the vast expanse of our solar system, only one moon possesses an atmosphere thick enough to walk through. Only one world beyond Earth has rivers that flow, lakes that shimmer, and rain that falls from clouds suspended in alien skies. That world is Titan, Saturn's largest moon, and it haunts the dreams of planetary scientists with a peculiar mixture of wonder and dread. Titan is not just another frozen satellite drifting through space. It is a world unto itself, larger than the planet Mercury, cloaked in a golden haze of nitrogen and methane that shrouds its surface from view. What we have discovered beneath that veil is extraordinary. Liquid methane lakes dot its polar regions, carved shorelines shaped by waves we will never hear. Mountains of water ice rise harder than granite in the cryogenic cold. Vast dune fields stretch across equatorial plains, sculpted by winds in an atmosphere 4 times denser than Earth's. Some scientists believe that beneath Titan's frozen crust lies a subsurface ocean of liquid water, perhaps containing the chemical building blocks of life. Others study its surface chemistry, searching for clues to how life might have begun on early Earth, frozen in time on this distant moon. Titan is irresistible. It is the closest analogue we have to our own planet in the outer solar system. And yet, that very similarity conceals a terrifying truth. The same features that make Titan scientifically invaluable, the thick atmosphere, the liquid cycles, the complex chemistry, transform it into one of the most physically hostile environments any spacecraft has ever attempted to land on. Before we go further, I'd love to know, where in the world are you watching this from, and what time is it right now? Drop a comment below. It's always fascinating to see this community span the globe. What lies ahead is a journey through the nightmare physics of landing on Titan. Every element that makes this moon remarkable also makes descending to its surface an engineering gauntlet unlike any other. As our spacecraft approaches Titan through the darkness of Saturn's domain, something extraordinary begins to happen. Long before we see the surface, long before we glimpse the methane lakes or the icy landscape below, we encounter the atmosphere. And it is not like any atmosphere we have known. Titan's atmosphere is impossibly thick. At the surface, it is 1.5 times denser than Earth's. To understand what this means is to imagine yourself not standing on solid ground, but submerged 15 feet beneath the ocean. The weight pressing down on you from all sides is not water, but air, heavy with nitrogen and methane, pressing against your spacecraft with a force that defies expectations. This is not the thin wisp of gas surrounding Mars, nor the crushing hellscape of Venus. This is something in between, something uniquely Titan. An atmosphere so dense that it reshapes our understanding of what a moon can be. The numbers tell a story that seems impossible at first. Titan's atmospheric pressure at the surface reaches 1.45 times that of Earth. This alone would not be surprising if Titan were a massive world, but Titan is small, far smaller than Earth. Its gravity is only 1/7 of our own. By all conventional logic, such weak gravity should not be able to hold an atmosphere this thick, and yet it does. The physics behind this paradox is as elegant as it is profound. Titan's low gravity means that atmospheric particles move more slowly, their escape velocity diminished. What would be flung into space on a larger world simply lingers. The atmosphere can extend outward, building layer upon layer without being compressed as violently as it would be on Earth. The result is an envelope of gas that stretches upward into space, 10 times higher proportionally than Earth's atmosphere. Where our own protective shell extends perhaps 100 kilometers before thinning to near vacuum, Titan's atmosphere reaches outward 600 kilometers or more, a gradual fade into the cosmic dark. For a spacecraft attempting to land, this creates a descent unlike any other in the solar system. There is no sharp boundary where space ends and atmosphere begins. Instead, there is a slow transition, a gradual thickening that pulls at the craft over hours, not minutes. The heat shield must endure not a brief, violent plunge, but a sustained marathon of friction. Every mile deeper into Titan's embrace brings more resistance, more heat, more pressure building against the hull. The composition of this atmosphere is equally remarkable. 95% nitrogen, the same element that dominates Earth's air, fills Titan's skies. But the remaining 5% is methane, and it is this methane that transforms Titan from merely exotic to profoundly alien. On Earth, methane exists in trace amounts, a greenhouse gas, a byproduct of life. On Titan, it is fundamental. It cycles through the atmosphere like water does on Earth, evaporating from lakes, condensing into clouds, falling as rain. This methane is not inert. It reacts with ultraviolet light from the distant sun, breaking apart and recombining into more complex organic molecules, tholins, which drift downward through the haze, painting Titan's atmosphere a uniform, eerie orange. These chemical reactions create unique hazards. Methane is highly flammable in the presence of oxygen, but Titan's atmosphere contains no oxygen. Instead, the danger is subtler. The organic compounds forming in the upper atmosphere are corrosive in ways we are still discovering. They coat surfaces, clog instruments, interfere with sensors. A spacecraft descending through this chemical fog must be designed not just to withstand pressure and heat, but to resist being slowly eaten away by the very air it passes through. And yet, within this terror lies something unexpectedly beautiful. Titan's dense atmosphere creates conditions that exist nowhere else in the solar system. The air is so thick, the gravity so low, that the mathematics of flight transforms entirely. Engineers have calculated that a human wearing artificial wings, simple mechanical extensions attached to the arms, could fly through Titan's skies. Not with engines or propellers, but by flapping. Like a bird, like Icarus, but without the sun to melt the wax. Imagine that moment. Standing on the surface of an alien moon, strapping on wings of carbon fiber and fabric, and simply lifting off. The atmosphere would hold you gently, the weak gravity releasing its grip with barely a protest. You would soar above methane rivers and mountains of water ice harder than granite, suspended in an orange haze that filters the sunlight into perpetual twilight. This is not a dream of distant centuries. This is physics. This is possibility. But that possibility comes at a cost. The same thick atmosphere that makes flight effortless makes landing extraordinarily complex. Heat shield design becomes an exercise in precision. Too light, and the spacecraft burns. Too heavy, and it cannot achieve the correct descent profile. The density of Titan's atmosphere means that parachutes deploy differently than they would on Earth. They open sooner, they drag harder, they must be stronger to survive the forces involved. The Huygens probe, which landed on Titan in 2005, used a sequence of 3 parachutes, each deployed at carefully calculated altitudes. The first slowed the craft from hypersonic speeds as it screamed through the upper atmosphere. The second stabilized the descent through the middle layers, where turbulence could tear the probe apart. The third guided it gently to the surface, drifting for more than 2 hours through the thick golden haze, before finally touching down on frozen ground. Every aspect of that descent was dictated by the atmosphere's density, the mission architecture, the timing, the structural integrity of every component. Engineers had to account for forces that built slowly but relentlessly, pressure increasing with every passing minute. There was no moment of sudden violence, no explosive entry like spacecraft experience at Earth or Mars. Instead, there was a long, grinding descent, a battle of endurance against an atmosphere that refused to let go. The density also creates acoustic phenomena unknown on Earth. Sound travels differently in Titan's thick air. It moves slower, carries farther, and lower frequencies dominate. If you could stand on Titan's surface and speak, your voice would sound deeper, muffled, as though you were speaking underwater. Thunder from methane storms would rumble with a bass resonance that could be felt in the chest, rolling across the landscape for hundreds of miles. This is the crushing atmosphere of Titan. Not crushing in the violent sense, not the bone-breaking pressure of Venus or the depths of Earth's ocean, but crushing in its persistence, its refusal to conform to expectations, its alien chemistry and physics that demand we rethink everything we know about planetary atmospheres. To descend through Titan's skies is to journey not just through distance, but through layers of possibility and peril intertwined. It is thick enough to fly through, dense enough to suffocate in, and strange enough to remind us that even air itself can be profoundly, terrifyingly alien. If the crushing atmospheric pressure is Titan's first warning, then temperature is its second act of cruelty. As our spacecraft descends through the orange haze, instruments begin to register something profoundly alien. The surface temperature of Titan averages negative 179 degrees Celsius, or negative 290 degrees Fahrenheit. This is not merely cold. This is a realm where the fundamental rules of matter itself begin to transform. At these temperatures, methane and ethane exist as liquids, pooling in vast lakes and seas that shimmer beneath the smog. Water ice, which on Earth melts into flowing rivers and gentle rain, becomes harder than granite. It forms the bedrock of Titan's continents, mountains frozen in geological permanence. The very substances that define our understanding of liquid and solid have exchanged roles. What flows on Earth is stone on Titan. What is solid here becomes vapor there. We are descending into a world where chemistry operates in reverse. But temperature is not just a measurement. It is a force that reshapes everything it touches. For spacecraft engineers, negative 179 degrees Celsius is not a challenge. It is a nightmare encoded in thermodynamics. Materials that function flawlessly on Earth become brittle and fragile in Titan's cryogenic embrace. Metals contract, sometimes cracking under their own stress. Rubber seals harden into rigid chips that crumble at the slightest pressure. Lubricants, designed to keep mechanical systems moving smoothly, freeze into solid wax, locking joints and gears in place like insects trapped in amber. Even the electronics that serve as the spacecraft's brain and nervous system begin to falter. Semiconductors, the building blocks of computer processors and sensors, behave differently at extreme cold. Their electrical resistance changes. Their response times shift. Engineers must account for these variations in every circuit, every wire, every transistor. A sensor calibrated for room temperature will give false readings in Titan's atmosphere unless specifically designed and tested for cryogenic operation. Batteries, which store the chemical energy needed to power systems, face perhaps the greatest challenge of all. Chemical reactions slow dramatically as temperature drops. At negative 179 degrees, the reactions inside conventional batteries essentially stop. The ions that shuttle back and forth between electrodes, creating electrical current, move sluggishly if they move at all. A battery that could power a rover for hours on Mars might last only minutes on Titan, if it functions at all. This is not a failure of engineering. It is a confrontation with the limits of chemistry itself. Yet the temperature challenge extends beyond the surface. During descent, the spacecraft must navigate a thermal gradient so extreme it defies everyday experience. In the upper reaches of Titan's atmosphere, temperatures hover near negative 200 degrees Celsius. As the probe descends, friction with the thickening atmosphere begins to generate heat. The spacecraft's heat shield glows, temperatures climbing to hundreds of degrees in seconds. Then, as velocity slows and the parachute deploys, cooling begins. The spacecraft must endure this violent swing from scorching heat to cryogenic cold, all while keeping its delicate instruments alive and functional. This is where thermal design becomes an art as much as a science. Every component must be insulated, heated, or allowed to cool according to a precise choreography. Too much heating and you waste precious power. Too little and systems freeze. The Huygens probe, which successfully landed on Titan in 2005, survived this ordeal through a combination of radioactive heating elements and multi-layered insulation that would make the finest Arctic expedition gear seem primitive by comparison. Radioisotope heater units, small capsules containing radioactive plutonium-238, were embedded within the probe's structure. As the plutonium decayed, it released a steady, reliable flow of heat. No moving parts, no fuel to burn, just the patient, unstoppable warmth of atomic decay. These tiny nuclear furnaces kept the electronics within operational range, even as the world outside plunged into temperatures that would freeze carbon dioxide solid. The insulation itself was layered like the skin of some deep-sea creature, adapted to crushing depths and freezing water. Multiple sheets of reflective material, separated by vacuum gaps, slowed the transfer of heat in and out of the probe. Every wire that passed through the insulation was a potential thermal leak, a bridge across which precious warmth could escape. Engineers wrapped cables in specialized materials, sometimes routing them through tortuous paths to minimize heat loss. The design was not elegant, it was survival. And yet, there is an unexpected grace note in this symphony of cold. Titan's thick atmosphere, the same atmosphere that creates pressure and obscures visibility, actually moderates the temperature somewhat. Without it, Titan would be even colder, exposed directly to the cryogenic vacuum of space and the distant, feeble warmth of a sun nearly 1 billion miles away. The nitrogen and methane clouds act as a blanket, thin and insufficient by Earth standards, but enough to prevent Titan from freezing into an even more inhospitable wasteland. It is a reminder that even in extremes, planetary systems seek balance. The atmosphere that suffocates also protects. The cold that threatens also preserves. To understand the horror of negative 179 degrees is to imagine standing in a place where your breath would freeze into snow before reaching the ground, where exposed skin would suffer frostbite in seconds, cells rupturing as the water inside them crystallizes into jagged ice. But no human stands on Titan's surface. Only machines venture there, machines built with exquisite care to withstand what flesh and bone never could. The spacecraft that descends through Titan's atmosphere carries within it a paradox. It must be robust enough to survive forces that would shatter ordinary equipment, yet delicate enough to measure faint chemical signatures and photograph alien landscapes through the gloom. Every sensor, every camera, every radio transmitter is a testament to human ingenuity pushed to its absolute limits. We are not merely exploring Titan. We are learning to exist there, however briefly, through our mechanical emissaries. The cold is not just an obstacle, it is a teacher. It reveals the boundaries of what matter can endure. It forces us to rethink assumptions about how machines operate, how energy is stored and released, how information is gathered and transmitted across the void. Every lesson learned in Titan's cryogenic hell informs the design of future probes, future missions to worlds even stranger and more remote. As our descent continues and the surface draws near, we carry with us the knowledge that temperature is not simply a number on a thermometer. It is the measure of how fast atoms vibrate, how readily molecules break apart and recombine, how easily energy flows from one place to another. On Titan, that flow slows to a crawl. Time itself seems frozen, locked in the grip of a cold so profound that only the universe's most patient processes endure. We are falling toward a surface where cold is not the absence of heat, but a presence unto itself, an element as fundamental as gravity, as inescapable as time. And yet, we descend anyway, armed with plutonium warmth and layered insulation, ready to touch a world where winter has reigned unbroken for 4.5 billion years. On most worlds, a storm is a complication. On Titan, it can be a catastrophe written into the physics of the planet itself. From orbit, Titan looks muted and featureless, its entire face wrapped in a deep orange haze. But beneath that smog lies something profoundly familiar, and utterly alien at the same time. A full, active hydrological system. Only here, the liquid that shapes the landscape is not water. It is methane. Titan is the only place in the solar system, other than Earth, where we've seen stable liquids pooled on the surface. Not frost, not transient flows that evaporate in sunlight. Real standing bodies of liquid, rivers, lakes, even seas. But at Titan's cryogenic temperatures, around -179 degrees Celsius, water is locked into a rock-hard crust. The role that water plays on Earth, rising as vapor, condensing as clouds, falling as rain, carving channels, filling seas, is taken over by hydrocarbons, methane and ethane. In our minds, the water cycle is something gentle and familiar. On Titan, the methane cycle is the same story told with different chemistry and darker consequences. Methane evaporates from the seas near Titan's poles, drifts into the thick atmosphere, condenses into clouds, and falls back as rain. Radar images from the Cassini mission reveal drainage networks, winding channels that look disturbingly like terrestrial river valleys. Some of them stretch for hundreds of kilometers, feeding into vast polar basins. When you see those images, you are not just looking at erosion. You are looking at alien weather that has been sculpting this world for millions of years. For a lander, that cycle is not an abstract process. It is an immediate hazard. Imagine descending through Titan's haze, instruments already battling the cold and the pressure, when the sky itself turns dark with hydrocarbon clouds. On Earth, a rainstorm means water, cooling air, maybe turbulence. On Titan, it means a downpour of liquid methane and ethane, fluids that on your homeworld would be flammable fuel. Here, in the oxygen-poor air of Titan, they do not ignite. They fall silently, soaking everything in a layer of cryogenic solvent. Models suggest that Titan's methane storms can be rare but violent. When they come, they may arrive as sudden cloud systems sprawling across entire regions, unleashing intense rainfall that can flood lowlands and send torrents surging down Titan's river channels. To a robotic probe with delicate joints, exposed sensors, and limited heat, this is not just weather. It is a chemical bath at temperatures that make metals brittle and plastics rigid. Landing in such a storm would be like touching down in the middle of a fuel spill at -179 degrees Celsius, with the fuel creeping into every crevice, altering friction, freezing into strange ices, and changing how your craft interacts with the ground. And sometimes, there may be no ground at all. Near Titan's North Pole lies Kraken Mare, one of the most haunting features in the Saturn system. It is not a lake by our standards. It is a sea, a dark, sprawling hydrocarbon ocean, larger in area than the Caspian Sea on Earth. Alongside it are other great bodies, Ligeia Mare, Punga Mare, each a basin of methane and ethane, fed by inlets and channels, surrounded by coastlines sculpted by waves and tides, driven by Saturn's distant pull. What happens if a lander, meant for solid terrain, touches down here? On Earth, a miscalculated ocean landing can be survivable. Water is familiar. We know how things float. We know how waves behave. Titan replaces that intuition with uncertainty. At its surface temperatures, liquid methane has a density and viscosity unlike anything we normally design for. It is less dense than water, more like a light, frigid oil. Ethane is denser, closer to a heavy hydrocarbon. Mixtures of the two create a liquid whose exact behavior, its waves, its splash, its spray, must be carefully modeled, not remembered from experience. Viscosity matters. It determines how easily something moves through a fluid, how quickly waves dampen, how a craft settles when it splashes down. Titan's seas, based on current measurements, may be surprisingly thin, low in viscosity, closer in feel to gasoline than to syrup. A lander hitting that surface at the wrong speed might not gently bob. It could punch through the surface film, sink deeper than anticipated, or oscillate wildly as it fights for equilibrium in a low-gravity, low-viscosity environment. Buoyancy is no less treacherous. Whether something floats is not just about how light it is, but how its average density compares to the fluid. On Titan, you must calculate buoyancy in a world where gravity is only 1/7 of Earth's, and the water is methane. A design that floats happily in terrestrial oceans might behave unexpectedly, sitting too high, too low, or destabilizing in slow-motion rolls that never quite stop. Mission planners cannot shrug and hope for dry land. They must treat every pixel of Titan's surface as a potential shoreline. Radar maps from Cassini show bright continents, dark seas, and everything in between. Marshlands, possible wetlands, evaporate deposits where liquids may come and go with the seasons. A targeted landing must account for the possibility that the chosen site, solid during one Titan year, could be slick, flooded, or even submerged in another. Titan's climate is not static. It evolves over its 29-year Saturnian orbit. Sunlight shifts, seasons change, and with them, the distribution of methane rain and lakes. A plain that looks safely dry at one time might be primed for inundation later. Selecting a landing site is not simply picking a coordinate. It is predicting an entire alien climate system decades in advance, then betting the mission on those predictions. Beneath these operational worries lies a deeper mystery. Titan's methane should not be there at all. Not in the quantities we see today. Ultraviolet light from the distant sun and energetic particles from Saturn's magnetic field constantly break apart methane molecules high in Titan's atmosphere. Over billions of years, this process should have stripped Titan of its methane, leaving only heavier organics and a dry, inert world. Instead, we find an atmosphere still rich in methane, actively cycling through clouds, rain, rivers, and seas. Something is replenishing it. Perhaps Titan hides vast underground reservoirs of methane and other hydrocarbons, slowly venting gas through cryovolcanism, ice volcanoes, where water and ammonia play the role of magma. Perhaps complex chemistry in Titan's interior is generating methane from primordial carbon, feeding the atmosphere over geological time. Or perhaps our timescale is wrong, and we are witnessing Titan during a brief, rare epoch when its methane cycle is temporarily active, a fleeting chapter in a much longer planetary history. Whatever the source, that hidden engine is the reason Titan has storms, rivers, and seas at all. It is the reason a lander must be engineered not just for rock, not just for ice, but for a world where the ground might abruptly turn to liquid beneath its feet, where the sky can open and pour down a rain of hydrocarbons, and where the shoreline is not just a boundary, but a moving target. To design for Titan is to accept that solid and liquid no longer follow Earth's rules. The familiar hydrological cycle has been rewritten in methane, and with it, all our instincts about what is safe, predictable, or stable on a planetary surface must be recalibrated. Here, weather does not merely inconvenience a mission. It defines whether a spacecraft lands on firm, icy ground or vanishes into a black, mirror-smooth sea of liquid methane under a sky that has never known blue. Beneath Titan's choking haze, there is no welcoming shoreline, no gentle beach of powdery snow. What waits is something far stranger. A world where water is not the source of life, but the skeleton of the landscape itself, where ice has forgotten how to melt and learned how to behave like stone. At Titan's surface, temperature of about minus 179 degrees Celsius, water is not just frozen, it is transformed. The molecules lock into a crystal lattice so rigid that the material rivals granite in hardness. What we on Earth carve with time and tectonics, Titan sculpts from frozen oceans. To land here is not to touch snow, it is to collide with rock made of water. Imagine standing on a shoreline where the bedrock beneath your feet was once a global ocean, now frozen solid into a planetary crust. The mountains on the horizon are not basalt or granite, but towering slabs of water ice. Cliffs that once might have floated as icebergs on a primeval sea now rise like petrified waves. This is the first horror of Titan's surface. Everything you recognize is built from something utterly unfamiliar. But this frozen planet is not uniform. Titan's face is a patchwork of extremes. Stretching for hundreds of kilometers are vast dune seas, as immense and unbroken as the Sahara. Yet these dunes are not made of sand. They are composed of microscopic grains of solid hydrocarbons, organic particles that have snowed out of the orange sky for millions of years. Each grain is formed high in the atmosphere, where methane and nitrogen are torn apart by sunlight and Saturn's radiation, rebuilt into longer and more complex molecules, and then slowly, silently, allowed to fall. Over time, these particles are sorted by Titan's winds. They gather into linear dunes that can tower more than 100 meters high, aligned with the sluggish atmospheric currents that circle the globe. To descend into these regions is to enter a desert made of plastic-like dust and organic soot, a place where every grain is a record of alien chemistry. Elsewhere, radar and imaging from Cassini hint at jagged uplands and possible mountains rising several kilometers above the plains. These are likely pure water ice massifs, cryogenic bedrock that has been lifted, fractured, and perhaps even resurfaced by internal processes. There may be cryovolcanoes here, icy analogues of terrestrial volcanoes, not erupting molten rock, but slurries of liquid water, ammonia, and other volatiles. Instead of glowing lava flows, imagine dark, viscous brines seeping and refreezing into new layers of crust, shaping Titan's surface in slow glacial bursts. This variety is not an artist's impression. For a brief, precious moment, we had a visitor on the ground. On January 14, 2005, the Huygens probe, carried by Cassini across nearly 1 billion miles of space, plunged through Titan's atmosphere and touched the surface. Its landing was not gentle. It hit the ground at roughly 5 meters per second, equivalent to jumping off a table. Yet the probe survived. The data it sent back in that final hour told a story that surprised almost everyone. Huygens did not land on a solid slab of ice, nor did it splash into a lake. Instead, its instruments recorded something in between. The surface resisted at first, as though there was a stiff crust. Then Huygens broke through, sinking a few centimeters into softer material beneath, like a boot pressing through a frozen top layer into wet sand or clay. For the engineers who had designed for nearly every possibility, this was a new category. Titan's ground, at least at that landing site, behaved like partially frozen mud. Hard enough to stop a spacecraft, soft enough to give way, and all of it at a temperature where, by Earth standards, everything should be brittle as glass. The images Huygens returned only deepened the mystery. Around the lander lay rounded pebbles and cobbles, some as large as fists, scattered across a seemingly dry plain. These rocks are almost certainly water ice, weathered and smoothed by long-vanished liquid, most likely methane and ethane that once flowed here like rivers. The colours suggested a world stained in dark orange and brown, not from rust, but from organic sludge. Everywhere on Titan, complex hydrocarbons are on the move. They fall from the sky, they settle into dunes, they dissolve in the methane lakes, they seep into the subsurface. Over time, they coat the ice in layers of gunk, tholin-rich deposits with unknown mechanical properties. Think of a landscape where every surface is painted with a mixture of wax, tar, and frozen smog. Rocks are no longer clean. Ice is never pristine. Everything is slick with chemistry. For a lander, that is a nightmare combination. Design teams must prepare for a surface that could be as unforgiving as granite, as treacherous as wet clay, or as yielding as a tar pit. All at the same landing site. Landing gear must be strong enough to strike rock-hard ice without shattering, but broad enough to avoid sinking into soft, organic dust. They must withstand impacts into frozen boulders, yet cope with the possibility of pancaking down into a crust overlying a mushy subsurface. And because Titan has lakes and seas of liquid methane and ethane, mission planners have to consider, what if the lander arrives in shallow liquid, or at the shoreline of a lake, or in a region that once was wet and is now crusted over with dried organic residue? On Titan, every scenario must be treated as likely. For Dragonfly, the upcoming rotorcraft mission to Titan, this problem becomes even more complex. It will not just land once, it will land again and again, hopping from site to site across dunes, plains, and possibly ancient river channels. Its skids must be prepared to touch down on frozen gravel, compacted hydrocarbon sand, or the residue of evaporated methane pools. It must be able to recover if one skid sinks while another strikes solid ice. No test chamber on Earth can perfectly recreate this environment. Every landing on Titan will be, in a sense, a controlled experiment in alien soil mechanics. Beneath these engineering challenges hides a deeper, more unsettling truth about Titan's surface. For all it's cold, it may be unexpectedly alive with motion. On Earth, we associate dynamism with heat, lava, plate tectonics, liquid water. Titan, locked in bitter cold, should be frozen solid and still. But the evidence whispers a different story. Some regions appear geologically young, with few impact craters. Certain features look smoothed over, resurfaced. There are hints of flows that do not match the patterns of dunes or river channels. These could be the traces of cryovolcanism, episodes where Titan's interior, warmed by radioactive decay and tidal forces from Saturn, pushes liquid reservoirs upward to the surface. If so, Titan's icy crust is not merely a static shell. It is a living skin, cracking, oozing and healing over eons. Hardened water ice mountains may crumble under the slow action of methane rain. Dunes may migrate. Organic deposits may be buried, melted, and refrozen. The world of ice is, paradoxically, a world of change. This is the surface horror of Titan. Not just its hostility, but its refusal to fit neatly into our categories. Rock that is water, sand that is carbon chemistry, mud that never thaws, a landscape sculpted by liquids that would boil away instantly on Earth, under a sky that never quite clears. To land here is to bring our fragile machines, and one day perhaps our fragile bodies, into contact with an environment that is not simply cold or harsh, but fundamentally alien in its physics. Titan's ground is not just something we have to survive. It is something we have to learn to understand, one careful, terrifying landing at a time. We begin our fall toward Titan not with a clear view of alien landscapes, but with a slow vanishing of the universe itself. Stars fade first, then Saturn's rings, then even the faint glint of our own spacecraft. Below us, there is no blue sky, no sharp horizon, only a deepening, uniform, burnt orange glow. Titan does not welcome visitors with vistas. It erases them. Its atmosphere is not just thick. It is clogged with a global shroud of photochemical smog, an organic haze so dense that visible light is swallowed long before it can reach the ground. If Mars is a dusty sunset, Titan is a permanent industrial twilight wrapped around an entire world. From roughly 200 kilometers above the surface all the way down to the ground, this haze forms stacked layers of particles, each one scattering and absorbing light. As we descend through them, the sunlight that does reach us has been filtered, diffused, and reddened until shadows barely exist. There is no clear down in the window, only a bright orange fog that thickens into something almost material. For a spacecraft, this is more than unsettling. It is a navigational nightmare. On Earth, landers can often rely on cameras and optical sensors to identify terrain, track motion, even choose safer places to touch down in real time. On Titan, that strategy fails almost completely. Long before we approach the surface, the haze blinds our eyes. We can point cameras downward, but all they see for most of the descent is a formless glow, like plunging into a cloud at dusk with no ground in sight. To understand why Titan is so opaque, we have to leave the cockpit and dive into its chemistry. High above the surface, in the upper atmosphere, Titan is bombarded by ultraviolet light from the distant sun and by energetic particles trapped in Saturn's magnetosphere. Up here, the air is dominated by nitrogen, like Earth's, but with an important twist. About 5% of it is methane. UV photons slam into these methane molecules and tear them apart. Hydrogen escapes, but the carbon stays, reacting with nitrogen and with itself. Simple molecules like CH4 are broken and rearranged into more complex hydrocarbons and nitriles. Ethane, acetylene, hydrogen cyanide, and countless others. These begin as gases, but as they combine into larger and larger structures, they start to stick together, forming microscopic solid and liquid particles, complex organic aerosols. Over time, they coagulate into clumps, fractal aggregates of carbon-rich material known collectively as tholins. The word comes from the Greek for mud, but on Titan, this mud is suspended in the air, forming a planet-wide smog bank. These tholin particles are incredibly effective at scattering visible light, especially the blue and green wavelengths that our eyes are most sensitive to. What survives the journey through this haze is mostly red and infrared, giving Titan its characteristic orange look. From orbit, the surface is almost impossible to see with normal cameras. From within the atmosphere, the effect is suffocating. Vision is replaced with permanent sunset. For a landing, that means one thing above all: we cannot trust our eyes. Instead, Titan demands that we navigate with instruments that can see what the light cannot. Radar becomes not just useful, but essential. Radio waves can punch through the haze that blinds optical cameras, bouncing off the surface and returning precious information about altitude, topography, and motion. This is why Cassini, orbiting Saturn, used radar imaging to map Titan's hidden face, revealing lakes, dunes, and channels beneath the orange veil. And it is why any future lander or rotorcraft must carry radar altimeters and possibly LiDAR systems to know how far they are from the ground when the surface itself is still invisible. We have already tried this once. On January 14, 2005, the Huygens probe plunged into Titan's atmosphere, trailing behind a heat shield and parachutes. For most of its descent, its cameras sent back images of almost nothing, just a uniform, fuzzy glow. Huygens was falling toward a landscape no one could see. Only in the final minutes, within the last few tens of kilometers, did the smog begin to thin enough for shapes to emerge. The haze parted, just enough for the cameras to glimpse dark branching channels, bright highlands, and what looked like a dried shoreline of some ancient methane sea. The surface revealed itself reluctantly, at the last possible moment, as though Titan was waiting to decide whether we were allowed to see it. For engineers, this delay is terrifying. There is almost no time to make adjustments once the ground appears. On Mars, landers can use camera-based navigation during the final descent, comparing real-time images with onboard maps. On Titan, by the time you can see clearly, it is essentially too late to negotiate with gravity. Your path must already be chosen, your landing sequence already locked in. The haze changes not just what we see, but how we arrive. In a clear atmosphere, a heat shield slams into compressed air that heats violently, glowing incandescent as it sheds energy. Titan is different. Its thick nitrogen-methane atmosphere and pervasive haze grains alter the physics of entry. The organic aerosols are small, but countless. As a spacecraft plows into them at hypersonic speeds, these particles interact with the shock layer around the heat shield. They can burn, crack, or even chemically react with the protective materials on the shield's surface. The result is a complex, layered heating profile that does not behave exactly like Earth's or Mars's. In some ways, Titan's atmosphere is gentler. Its density slows you earlier, spreading heating over a longer time. Peak temperatures can be lower than a similar entry at Earth, but the duration of stress is extended and the chemistry is unfamiliar. Engineers must design materials that can survive not just high heat, but prolonged exposure to a reactive organic plume, burning smog essentially, wrapped around the capsule as it falls. It is a quiet violence. From inside the spacecraft, we would see none of it. Only rising plasma temperatures on the instruments, a flare of heat on sensors, and then the dull roar of parachutes opening into a sky with no features. Yet, within this nightmare for navigation and engineering lies something profoundly tantalizing. Those same haze particles that blind us may be assembling chemistry that points toward life. Tholins are not random dirt. In laboratory simulations, where researchers bombard Titan-like gas mixtures with UV light or electrical discharges, the resulting gunk, those tholins, contain amino acid precursors, nucleobase-like compounds, and a zoo of complex organics that resemble prebiotic chemistry. On Titan, these molecules fall like a constant, planet-wide drizzle. They settle onto ice, into lakes, and along river channels. Over geological time, the surface becomes coated in a dark, organic mantle. It is messy. It is chaotic. And it might be the kind of chemical mess that, under the right conditions, can take the first steps toward life. So as we descend blind through orange smog, we are not just pushing through an obstacle. We are falling through a global chemistry experiment that has been running for billions of years. Every haze particle that slams into our heat shield, every speck that clings to our instruments, is a message from a different kind of prebiotic world. One where water is frozen, methane reigns, and organic chemistry reigns in the sky. Titan forces us to accept that exploration here will never be straightforward. We must land where we cannot see, rely on radar instead of vision, and design hardware to survive a descent through burning, reactive fog. But in doing so, we gain access to a place where the very haze that hides the surface may hold the clues to how chemistry becomes biology. In the end, the terror of landing blind through orange smog is inseparable from Titan's greatest promise: To reach the ground, we must pass through the veil. And on Titan, the veil itself is the story. By the time we reach Saturn, distance is no longer just a number. It becomes a form of exile. Saturn orbits, on average, over 1 billion kilometers from Earth. Even at its closest, that separation is still staggering. About 1.2 billion kilometers of empty space lie between us and Titan. At that range, light itself, our fastest possible messenger, needs roughly 70 to 90 minutes to make the journey one way. A radio signal leaves Earth, racing at 300,000 kilometers per second, and then simply vanishes into the dark for over an hour before it ever brushes the edge of Saturn's domain. For a lander falling through Titan's atmosphere, this delay changes everything. On Earth, we are used to control. A pilot nudges a joystick and a plane responds. An engineer adjusts a thruster command, and a spacecraft obeys in near real time in low Earth orbit. Even missions to the Moon feel interactive. A few seconds of radio delay is inconvenient, but manageable. You can have a conversation with a machine. On Titan, there is no conversation. There is only a monologue, spoken long ago. When a probe begins its descent toward Titan's smog-choked surface, every decision it makes must be made alone. By the time the probe senses that it has touched the upper atmosphere, the signal carrying that information has not yet even begun its journey to Earth. When it feels turbulence, when its parachutes deploy, when its instruments wake up and taste alien air, back home, mission control is still living in the past, receiving data from a different moment of the descent. Real-time control is not merely difficult. It is physically impossible. Imagine you are in charge of this landing. The probe hits an unexpected downdraft. Its descent rate suddenly doubles. On Earth, you would command the parachute to adjust, deploy a backup, change the attitude, fire small thrusters, anything to slow the fall. But on Titan, by the time your instruments report that something has gone wrong, the event is already history. Those crucial seconds of chaos played out over an hour ago, and even if you could craft the perfect corrective command instantly, it would not reach Titan until another hour had passed. 2 hours. That is the cycle of cause and effect at Saturn's distance. An hour to learn that something happened, an hour to respond. For a probe whose entire descent lasts just 2.5 hours, that delay is a verdict. If something critical fails, there is no rescue. There is no improvisation. There is only silence at the bottom of an alien sky. To survive in such isolation, Titan landers must become something more than remote-controlled machines. They must be robotic explorers with a kind of pre-planned judgment, autonomous systems that follow a script but can also react within strict boundaries. They must decide when to fire heaters, when to shift how they sample the air, when to switch antennas, when to declare that they have, finally, reached the surface. And yet, even this autonomy exists within another layer of complexity, the relay. Titan does not speak to us directly. Radio waves leaving its shrouded atmosphere are faint, easily lost in the noise of cosmic radiation and the vastness in between. So most missions do not send a lander alone. They send a companion, an orbiter that circles Saturn or Titan itself and acts as a celestial middleman. The lander whispers upward. The orbiter listens, records, and then turns its stronger antenna toward Earth, hurling those precious bits of information across the void. This setup solves one problem and creates others. The orbiter must be in the right place at the right time, sweeping over Titan's sky as the probe descends. Its instruments must be awake, its receivers aligned, its software prepared to catch a fragile stream of data that will never be repeated. A slight timing mismatch, a misconfigured instrument, a misunderstood interface, and the lander's voice is lost, even if the landing itself succeeds. We came close to learning this the hard way. On January 14, 2005, the Huygens probe plunged into Titan's atmosphere, carried there by the Cassini spacecraft. For the first time in history, a human-made object would touch the surface of this mist-shrouded moon. Huygens had one chance, just a few hours of power, to sample the air, snap images, and send its discoveries upward to Cassini as it flew past overhead. But hidden inside the mission was a quiet flaw. A configuration issue in Cassini's software meant one of its key receivers was not set up to properly record part of Huygens' signal. The mistake was subtle, buried in the complexity of instruments, modes, and assumptions made years earlier. There would be no second attempt, no patch, no last-minute fix. By the time anyone on Earth realized what had happened, Huygens would already be dead on Titan's surface. The only reason we did not lose almost everything is that Huygens had a second channel, a backup way of speaking. Much of the data, including those haunting orange-hued images of Titan's sky and surface, came through that surviving link. The mission was saved, but the near failure left a chilling aftertaste. We very nearly sent a probe to an unknown world, watched it vanish into the haze, and heard almost nothing in return. That is the terror of autonomy at Saturn's distance. We must trust hardware we cannot touch, software we cannot debug in real time, and decisions we can only reconstruct long after they are made. When a probe falls through Titan's orange clouds, it is executing a plan written years earlier by people who will never see Titan with their own eyes. Months of simulation stand in for minutes of reality. Future missions push this further still. Dragonfly, NASA's planned nuclear-powered rotorcraft, will not just land on Titan, it will fly across it. Hop by hop, it will lift itself into the thick, frigid air, drift over dunes of hydrocarbon sand, and descend to new landing sites kilometers away. Each flight will unfold under the same implacable delay, 70 to 90 minutes of silence between command and consequence. Dragonfly cannot ask, "Is it safe to land here?" and wait for an answer. It must look, decide, and descend entirely on its own. Its cameras and sensors will scan for obstacles. Its software will evaluate terrain. Its systems will assess whether the wind is tolerable or treacherous. Only after the fact will Earth receive a delayed playback of its choices, a mission review of actions already taken on a world we still barely understand. In a very real sense, Dragonfly will be flying blind, not because its instruments are closed, but because we are. Our oversight is severed by the physics of light itself. We do not guide it moment to moment. We author its instincts and then let them run, hoping we have anticipated enough of Titan's moods. This is the isolation factor of Titan. It is not just the cold, the pressure, or the distance. It is the enforced loneliness of machines acting without us, the recognition that in these far reaches of the solar system, exploration is no longer a tethered operation. It is an act of trust. Trust in equations written decades before landing. Trust in circuits that will wake in a sky no human has ever breathed. Trust that when the data finally reach us, hours after the events they describe, we will be reading not an obituary, but a diary of survival on a world more alien than any desert on our own. The moment we touch Titan's atmosphere, the clock starts ticking in a way that feels unfamiliar, almost wrong. On most worlds we've visited, entry and landing are brutal, compressed into minutes of violence and uncertainty. On Mars, engineers call it the 7 minutes of terror. 7 minutes where everything happens at once. Blazing entry, parachute deployment, rockets firing, and finally, if all goes well, a soft impact on alien soil. Titan does not give us 7 minutes. It gives us nearly 2.5 hours. When the Huygens probe arrived at Titan in 2005, it spent 2 hours and 27 minutes simply falling. Not tumbling uncontrollably, not crashing through thin air, but drifting down in a long, controlled surrender to gravity. What sounds gentle on paper is, in reality, a new kind of nightmare. Because here, terror is not a spike. It is a plateau. A sustained, unbroken descent where anything can go wrong, and where every second is another chance for the unknown to interfere. The reason lies in the physics that make Titan so strangely deceptive. Titan's gravity is only about 1/7 that of Earth. If you dropped a rock there, it would fall lazily, as if the moon itself were reluctant to let it go. But the atmosphere tells a different story. Titan's air is not a thin veil like Mars's. It is dense, heavy, closer in surface pressure to Earth's oceans than to the vacuum of space. At the ground, the pressure is about 1.5 times that of sea level on Earth, and the air is 4 times denser. This combination, weak gravity, thick air, reshapes the meaning of falling. On Earth, terminal velocity for a human skydiver, arms and legs spread wide, is around 120 miles per hour, or 190 kilometers per hour. On Titan, the same body, in the same position, would drift down at something closer to jogging speed. A person could literally strap on wings and fly, not figuratively, but in the strictest physical sense, flapping or gliding through methane-rich air like some slow-motion, frozen bird. For a probe, the same physics means that it doesn't plummet. It floats. It breaks itself simply by existing, its heat shield and shell turning speed into drag long before the first parachute ever opens. At first, this sounds comforting. Lower speeds, gentler forces, more time to react. But more time is also more risk. The descent through Titan's atmosphere is not a straight line. It is a journey through layers that change slowly, not just in temperature and density, but in motion. Titan's atmosphere doesn't rotate in perfect lockstep with its surface. High above, winds scream eastward, racing around the moon faster than Titan itself spins. This phenomenon, called superrotation, means that as you fall, the air beneath you is not the same air above you. You are passing through a stacked, shifting flow of gas that is in many ways more like a slow, planetary river than a mere blanket of air. To survive this descent, Huygens, and any future lander, must choreograph a complex dance of parachutes. It begins violently. The probe slams into the upper atmosphere at over 6 kilometers per second, shield first, compressing nitrogen and methane into a blazing bow wave. For a few frantic minutes, Titan briefly behaves like every other world we know. Heat, shock, plasma. But because the air is thick, the probe slows quickly. By about 160 kilometers above the surface, it has bled off enough speed for the first critical event, parachute deployment. The drogue chute is small, almost modest compared to what comes next. Its job is not to slow the probe to a safe landing speed. Its job is to stabilize, to pull Huygens away from its heat shield, to give the craft a sense of orientation in a sky it cannot see. In the orange haze of Titan, there is no horizon, no clear up or down, only data. The drogue is the first tether to order in an atmosphere that wants to twist and spin. Then comes the main parachute. This is where Titan's slow-motion nature becomes obvious. The main canopy is huge, deliberately oversized, turning Huygens into a drifting seed in a planetary sky. Under this chute, the probe falls so slowly that, left unchanged, the descent would go on far too long. Hours more, maybe longer. At first, this seems like a blessing for science. More time in the atmosphere means more measurements, more profiles of temperature, wind, and composition. But there is a brutal constraint pressing against that dream: the battery. Huygens carried no nuclear power source, no long-lived reactor humming quietly in the dark. It depended entirely on chemical batteries, pre-charged on Earth, sealed and finite. Every volt was precious. Every minute in the air, every extra kilometre of leisurely descent was a direct subtraction from the time it could spend alive on Titan's surface. The mission was a race between curiosity and chemistry, so a decision was made that feels paradoxical for a world defined by slowness. Halfway down, Huygens cut its main parachute loose. In its place, a smaller parachute deployed, intentionally speeding up the fall. Engineers had to accept a harsher landing zone profile in exchange for more time on the surface and more margin against the unknown. The probe, which had been gliding down like a feather in syrup, began to sink more firmly, trading altitude for seconds of future science. All of this happens while Titan's winds are pushing, pulling, and twisting the probe in ways that are almost poetic in their complexity. At higher altitudes, super-rotating winds whip Huygens sideways at over 400 kilometers per hour, dragging it far from the vertical line below the entry point. Deeper down, those winds begin to fade, turning into gentler breezes closer to the surface. The descent is not a straight drop, but a long horizontal drift, a silent ride carried by an atmosphere that moves faster than the ground beneath. For mission planners, this is both an opportunity and a problem. The slow fall allows instruments to map Titan's winds with exquisite detail, turning the 2.5-hour descent into a vertical weather profile through an alien sky. But for navigation and landing, it is a nightmare. The ground track, where the probe will actually hit, is not a fixed target. It is a shifting projection through a moving fluid. You can aim for a region, you cannot choose a spot. And through all of this, the battery timer continues its relentless countdown. By the time Huygens approached the murky boundary where atmospheric haze gives way to a dim, reddish landscape, it had already spent more time falling than any Mars mission spends from entry to touchdown and initial surface checks combined. On Mars, terror is a sprint. On Titan, it is an endurance event. Every parachute deployment is a potential failure point. Every minute of radio contact is a chance for signal loss. Every shift in wind, every unexpected layer of haze, every tiny malfunction has an enormous canvas of time in which to happen. The slow descent magnifies the unknowns, stretching them out until they feel almost infinite. And yet, that same slowness is what makes Titan uniquely reachable for fragile machines, and perhaps someday for humans. The atmosphere cushions, cradles, buys time where other worlds offer only a single brutal plunge. Titan asks us to endure not a single instant of fear, but a prolonged immersion in it. 2.5 hours of controlled falling. 2.5 hours of trusting physics we have never experienced firsthand. In that long, drifting descent, Titan reveals its true character. Not violent, but inexorable. Not explosive, but patient. A world where even gravity seems to move in slow motion, yet where the consequences of each decision echo for hours. By the time the probe's feet, or one day human boots, finally press into that frozen, hydrocarbon-soaked ground, the descent will not feel like a simple landing. It will feel like emerging from a drawn-out, suspended uncertainty. Titan does not just test our technology, it tests our ability to wait, to watch, and to trust that, over the span of hours in an alien sky, every carefully planned action will unfold exactly as intended. For most of human history, worlds like Titan existed only as distant lights in the sky, objects to be named, charted, and admired from afar. But now, standing on the shoulders of Huygens and Cassini, we are preparing to do something far more radical. We are not just dropping a probe and hoping it survives a single descent. We are sending a machine that will arrive, land, rise again, and roam. Its name is Dragonfly. Dragonfly is unlike any spacecraft we have ever sent to another world. It is not a rover that crawls slowly across a hostile surface. It is a nuclear-powered drone, a quadcopter scaled up to the size of a small car, designed to leap from place to place across Titan's frozen landscape. Where other missions cling to a single landing site, Dragonfly will explore a world. In almost every way, Titan seems like the last place you would choose to fly. The temperature is low enough to turn most materials brittle. Hydrocarbon, sand, and organic dust drift across the surface. The sky is a thick orange smog. Sunlight is weak, scattered, and often completely absent. But hidden inside all of those difficulties is a strange, almost paradoxical gift. On Titan, flying is easier than it is on Earth. Flight is a negotiation between lift and gravity. On our planet, thin air and relatively strong gravity mean airplanes must move fast and work hard to stay aloft. Titan rewrites that equation. Its atmosphere is 4 times denser than Earth's at the surface, yet its gravity is only about 1/7 as strong. For a vehicle with wings or rotors, this combination is almost dreamlike. It is as if nature quietly built a test range for flying machines on an alien moon. If you could stand on Titan in a pressurized suit and strap on wings, you could, in principle, glide with a gentle running start. For a drone, the advantages are even more dramatic. Dragonfly can generate more lift with less power, hover for longer, and land with a cushion of thick air beneath it. The nightmare that Titan's atmosphere creates for parachutes and landers becomes a rare advantage for powered flight. NASA's planners looked at Titan's numbers, density, gravity, wind, temperature, and realized something astonishing. The same physics that make landing terrifying make exploring by air almost ideal. Dragonfly's mission profile reflects that revelation. After a years-long journey through the outer solar system, it will plunge into Titan's atmosphere protected by a heat shield, then slow with a parachute, then finally ignite its rotors and perform a controlled powered landing near Titan's equator. That first touchdown is only the beginning. Once on the surface, Dragonfly will rest, listen, and learn. It will deploy instruments, sample the local terrain, taste the air, and study the chemistry of the ground beneath it. Then, when conditions are right, it will do something no other mission has ever done on another world. It will take off again. Dragonfly will move in a series of hops, short flights of a few kilometers, then longer legs of up to tens of kilometers at a time. Over the course of its planned mission, this strange aircraft could cover more ground than all Mars rovers combined, crossing dunes, plains, and possibly the edges of ancient impact craters. Each landing site becomes a new laboratory, each flight a bridge between radically different environments. On Mars, distance is a hard-won prize measured in meters per day. On Titan, distance becomes a thread. Dragonfly can weave across a continent of alien chemistry. But such mobility comes at a price. A rover must survive one landing. Dragonfly must survive many. Every time it descends, it must trust Titan's atmosphere again, its winds, its turbulence, its invisible currents. It must extend its landing skids into uncertain terrain, organic sand that may shift under its weight. crusted surfaces that may crack, hidden rocks buried beneath hydrocarbon snow. No simulation on Earth can perfectly reproduce what Titan's regolith will feel like when metal meets frozen chemistry. Dust and organics present their own menace. Over years of operation, tiny particles may cling to Dragonfly's surfaces, accumulate on sensor windows, work their way into mechanisms designed for near absolute cold. On Earth, dust is an inconvenience. On Titan, where temperatures hover near -179 degrees Celsius and materials behave differently, dust and frost can become slow, patient saboteurs. And then there is time. Dragonfly is not coming for a fleeting visit. It is designed for long-term surface operations in an environment that has never seen anything like it. Temperature cycles between Titan's long days and nights will stress its structure. Slow, creeping deposition of methane ices and other volatiles may reshape its landing pads and instruments over months and years. The same thick air that supports graceful flight may, over time, erode delicate sensor readings, coating and cooling everything. To endure all of this, Dragonfly carries a heart of radioactive heat. At Titan's distance from the Sun, solar power is nearly useless. The sunlight that reaches the surface is already dim, then filtered through hundreds of kilometers of haze. A solar-powered drone would struggle to charge its batteries, especially during Titan's long polar seasons of darkness. The solution is one humanity has turned to again and again in the outer solar system: radioisotope power. Dragonfly uses radioisotope thermoelectric generators, RTGs, which convert the heat from the natural decay of plutonium-238 into electricity. These generators are simple, solid-state devices with no moving parts, capable of providing steady power for years. On Titan, they do double duty. They generate the electricity Dragonfly needs to run its computers, instruments, and rotors, and they provide precious warmth, keeping its systems from freezing solid in the cryogenic air. In a sense, Dragonfly carries its own tiny artificial sun. Not bright enough to light the sky, not hot enough to melt the ice beneath it, but sufficient to sustain a pocket of Earth-like temperature inside a shell of metal and composite. Surrounded by methane snow and hydrocarbon dunes, Dragonfly will be a warm, humming anomaly in a world that has been frozen for billions of years. All of this effort, all of this engineering audacity is driven by a set of questions that reach far beyond Titan itself. What does chemistry look like in a place where water is rock and methane is rain? What molecules form when simple hydrocarbons are bathed in cold, slow energy under a thick, protective atmosphere? Do the building blocks of life, complex organics, prebiotic molecules, assemble themselves in Titan's lakes and dunes, waiting for liquid water and heat that may never come? Dragonfly will carry instruments capable of sampling Titan's surface materials, analyzing their structure, and searching for patterns that hint at prebiotic chemistry. It will sniff the air for complex organic molecules, measure the weather, map the radiation environment, and probe the properties of Titan's crust. In the best-case scenario, it may even detect biosignatures, chemical fingerprints that, while not proof of life, would show that Titan's chemistry has taken steps in that direction. No one expects Dragonfly to roll up to a Titanian forest or a methane ocean teeming with visible creatures. The expectations are subtler, and in some ways, more profound. We want to know how far chemistry can go on its own in a world that has the ingredients of life, but not necessarily the conditions we are used to. We want to understand whether Titan is a frozen archive of Earth's prebiotic past, preserved in slow motion. Dragonfly represents the best of our current engineering imagination aimed at that mystery. It is robust, but not invincible. Its systems are carefully tested, but they will face combinations of cold, chemistry, and weather we can only approximate. No mission to Titan can be guaranteed. There are unknowns we will only discover when we arrive, and yet, that is the point. With Dragonfly, we are not just dropping a flag onto an alien shore. We are sending a flying laboratory into a world that challenges everything we think we know about habitability, chemistry, and the possibilities of nature. It is an audacious answer to Titan's terrifying physics, not to shy away, but to adapt, to learn, and to use those very conditions to our advantage. If it succeeds, Dragonfly will not just rewrite the story of Titan. It will redefine how we explore hostile worlds. By landing, listening, and then taking to the air again and again, across the frozen orange dusk of a moon that might hold echoes of our own beginnings. We have dropped robots into Titan's darkness. We have tasted its air with instruments, skimmed its lakes with radar, and mapped its dunes from orbit. But somewhere behind every robotic mission is an unspoken question. Could a human being ever stand there? Could a person take a step onto that frozen shore, look up through the orange haze and say, "I am on Titan"? To even ask this is to stretch time. We are not talking about the next mission cycle or the decade after that. We are peering into a future that may be many decades, perhaps centuries away. But the physics is not fantasy. There is no warp drive required, no new laws of nature to invent. Titan does not forbid us with impossibility. It challenges us with endurance. The first obstacle is distance, not in miles, but in years of a human life. With a technology we have actually flown, Titan is a 7-year commitment just to arrive. Cassini took almost 7 years to reach Saturn's realm, threading its way through gravity assists from Venus, Earth, and Jupiter to steal speed from the orbits of worlds. A crude Titan ship would need something similar. A slow, careful fall down the gravitational staircase of the solar system. For an astronaut, that means a mission timeline unlike anything we've ever attempted. The Apollo missions lasted days. Stays on the International Space Station stretch months. A round trip to Titan, including time in orbit, surface operations, and the long curve back toward the inner solar system, could easily consume a decade. You would leave Earth as a middle-aged explorer and return as someone whose world has moved on without you. Children would grow up. Nations would change. The constellations would look the same, but the story beneath them would not. Inside the ship, time would be measured differently. Not in launch windows and splashdown schedules, but in maintenance cycles and psychological seasons. For 7 years, the crew would wake in artificial gravity, or perhaps in slow spinning habitats that mimic weight, knowing that every sunrise they see is a simulation. Beyond the hull, there is no quick abort, no fast flight home. At Titan distances, rescue is not a plan. It is a myth. And yet, if we accept that voyage, if we accept that human beings can sustain such missions, Titan itself offers a paradoxical welcome. Because once you actually arrive, once you fall through the atmosphere and reach that alien ground, survival becomes a very different kind of problem. On airless worlds like the Moon, the universe is raw and exposed. Radiation from the sun and deep space slams directly into the surface. Every excursion is a race against your suit's lifetime and your body's tolerances. Mars offers only a thin whisper of air, barely any protection at all. But Titan is a fortress. Its atmosphere is thicker than Earth's, almost 1.5 times the pressure at sea level. Above your head is a sky hundreds of kilometers deep, rich with nitrogen and haze, scattering and absorbing the lethal particles that would shred DNA on unprotected worlds. Saturn's immense magnetic field extends outward like an invisible shield, deflecting radiation long before it can even reach Titan's clouds. Step onto Titan's surface, and for the first time on another world, you are not under a cosmic bombardment. You are, in a strange way, safer than on the moon. The danger has simply changed form. Here, the enemy is cold so intense that metal behaves like stone, and air itself becomes a reservoir of liquid methane. Your habitat would be a warm island in an ocean of cryogenic night. Inside, conditions must be stubbornly familiar. Earth-like air, Earth-like pressure, temperatures held steady against a world that wants to drag everything down to minus 179 degrees Celsius. The physics of that challenge is simple and merciless. Every square meter of your habitat, every pipe, every window, every airlock is a battlefield between heat and vacuumed cold. Insulation becomes sacred. Waste heat, a nuisance on other worlds, becomes a resource. The warmth from electronics, from life support, even from human bodies themselves, can be recaptured, recycled, used to keep walls from freezing solid. On Titan, overheating is not your enemy. Losing a single watt too many might be. The suits that carry humans outside would look less like the thin shells we imagine from science fiction and more like mobile furnaces. Unlike on the Moon or Mars, you don't need enormous pressure to protect against vacuum. Titan already gives you pressure. The suit could operate close to Earth normal, simplifying some of the worst design headaches of EVA systems. But everything else becomes extreme. Every joint must remain flexible at temperatures that can lock ordinary materials into immobility. Every visor heater must keep methane from condensing as frost across your view. Cooling systems, vital on the Moon and Mars to bleed off metabolic heat, now work in reverse. You are not trying to dump heat quickly into a vacuum. You are trying to hang on to it, carefully, while still keeping the human inside from overheating in a walking thermos bottle. The suit is no longer just a barrier. It is an artificial environment inside another artificial environment. A bubble of Earth nested within an orange world. Outside that shell, gravity offers an unexpected grace. Titan's surface gravity is about 1/7 of Earth's, even gentler than our Moon's pull. A person encased in heavy suit and life support could leap effortlessly, carry massive equipment like it was camping gear, build habitats with motions that feel like slow-motion ballet. Heavy lift cranes might become optional. On Titan, human muscles are almost overkill, yet for all its physical accommodations, Titan presents a challenge harder to engineer away: the human mind. Imagine a sky without stars. Titan's orange smog is thick enough that direct sunlight rarely reaches the surface. Daylight is a dim, muted glow, more like late evening on Earth than midday. Nights are not truly black, only deeper shades of rust and amber. Saturn, immense and ringed, might sometimes loom faintly behind the clouds, but never in the sharp relief we see in artists' impressions. Reality is softer, blurrier, more enclosed. Living there would mean trading the blue dome of Earth for a permanent monochrome. Weeks would pass without ever seeing a true shadow cast by a sharp sunbeam. Month after month, the outside world would look the same: frozen lakes, dark dunes, low rolling terrain smoothed by methane rain and hydrocarbon snow. Beautiful in its own way, but also alien in a slow, creeping manner that could erode the psyche. And always there is the number, silent in the back of every mind: 1.2 billion kilometers. The radio calls home take over an hour for a round trip. A joke from Earth arrives long after the moment has passed. A child's birthday greeting comes with the delay of a different world's orbit. The crew is not simply distant. They are temporally displaced, living in a conversation that never quite sinks, like talking to the past and the future at once. Homesickness, on Titan, would not just be missing people. It would be missing color, missing air that you can breathe without ritual, missing the unconscious knowledge that there is a world outside where you could walk out the door and simply exist. On Titan, existence is always conditional, always bracketed by engineering, always mediated by pressure walls and heat exchangers. And yet, for all its severity, there is something deeply human about the idea of walking on Titan. It is not merely surviving in an extreme environment. It is choosing to live there, to take our fragile biology and wrap it in layers of technology and trust, then set it down on a world that has never known a footprint. The physics tells us that someday it is possible. Advanced propulsion could shrink the 7-year transit to something more manageable. Nuclear power systems could run habitats and suits indefinitely, turning waste heat into life. Closed-loop ecosystems, grown from the lessons of decades in orbit, could support small communities beneath Titan's icy crust or domed over its plains. For now, it remains a thought experiment, a future chapter unwritten. But it is a chapter grounded in real numbers, real equations, real materials. Titan does not kindly invite human beings, but it does not absolutely reject us either. It stands at the edge of what we can imagine enduring. A world where the terror is not in instant death, but in the long, deliberate work of staying alive. If we ever choose to send people there, it will not be for comfort. It will be because some future generation decides that understanding Titan, touching it, walking its frozen shores, and listening to the whisper of methane rain against a human-built window is worth years of distance and a lifetime of adaptation. In that decision, we would do more than conquer another frontier. We would prove that, even in a universe of crushing cold and endless dark, there are places where human curiosity can carve out a small, warm pocket of existence and call it home, if only for a while. For all the dangers, for all the ways Titan seems determined to break our machines and freeze our dreams solid, there is one simple truth that keeps us coming back. This world might remember how life begins. On Earth, the record of our origin has been largely erased. Plate tectonics, erosion, and 3.5 billion years of chemistry have overwritten the earliest pages of our story. The first fragile molecules that learned to copy themselves, that danced on the edge between chemistry and biology, are long gone. But Titan is different. Here, the clock is set to an earlier time. The air is thick with nitrogen, laced with methane and complex organics, an eerie chemical echo of what many scientists think Earth's atmosphere looked like before life transformed it. While our planet moved on, blooming into oxygen and oceans, Titan seems to have remained in a kind of arrested development, a frozen, preserved laboratory of prebiotic chemistry, running experiments nature no longer performs at home. High above the surface, sunlight and Saturn's magnetospheric particles shatter simple molecules apart. Carbon, hydrogen and nitrogen recombine into increasingly intricate structures, hydrocarbons, nitriles, tholins, falling like slow orange snow toward the ground. Every grain of that material is a question. Given enough time, enough energy, enough complexity, does chemistry inevitably become biology? We cannot wind Earth back to its first dawn, but we can go to Titan, where the atmosphere itself may be a living archive of the steps between a lifeless world and a living one. Beneath that atmosphere, another secret may be waiting. Titan is not just rock and ice. Beneath its rigid, frigid crust, the evidence points to a hidden ocean, a global sea of liquid water mixed with ammonia, buried under tens of kilometers of ice. Radar from Cassini, tiny wobbles in Titan's rotation, hints from its gravity field. Together they draw the outline of an unseen world, warm compared to the surface, shielded from radiation, stable for billions of years. On Earth, wherever we find liquid water, we find life. In boiling vents at the seafloor, in subglacial lakes sealed off for ages, in the pores of rocks deep underground. If Titan's ocean exists, it has had time, energy from tidal flexing and radioactive decay, and a steady supply of organic material drifting down from above. There, in the dark, chemistry has had billions of years to explore what is possible. We don't know if anything swims in that hidden sea. We don't know if cells could form under those conditions, or if metabolism could ignite in such alien brine. But the possibility transforms Titan from a cold curiosity into something more profound, a potential second cradle of life in one star system. And the story might not end in the depths. On the surface, lakes and seas of liquid methane and ethane pool in Titan's polar regions, carving shorelines, feeding rivers, evaporating into clouds, raining back down again in a slow, frigid cycle. It is an alien hydrological system, running not on water, but on hydrocarbons chilled to -179 degrees Celsius. For terrestrial life, this is death, far below the freezing point of every known cell. Yet some researchers ask a forbidden-sounding question. Must life use water at all? Water is a remarkable solvent, but it is not the only one. In principle, liquid methane can dissolve certain molecules, enable reactions, and transport chemical energy. Some theoretical studies suggest that membranes, flexible structures like our cell walls, could form in liquid methane from entirely different molecules, azotosms instead of liposomes, built from nitrogen-bearing organics instead of phospholipids. No one is claiming Titan's seas are teeming with methane swimmers. The chemistry is slow at such low temperatures, the margins for complexity thin. But even the barest hint of surface life using methane instead of water would shatter one of our deepest assumptions, that habitable always means Earth-like. Searches for life on Titan are therefore not just about finding something alive. They are about asking whether life, in any form, is a universal pattern that emerges wherever conditions allow, or a rare accident tied tightly to liquid water and mild temperatures. Titan is the experiment nature has been running for ages in the cold, at the edge of plausibility. And Titan's significance stretches far beyond our own solar system. When we look at exoplanets, worlds orbiting distant stars, we are increasingly finding atmospheres that are thick, hazy, and rich in unfamiliar molecules. Mini-Neptunes shrouded in clouds. Super-Earths wrapped in methane and nitrogen. Some may be Titan-like in key ways, dense air, high-altitude hazes, complex organic chemistry in play. But we only see them as a few pixels, a faint dip in starlight, a subtle fingerprint in a spectrum. To interpret those faint signals, we need a template, a real physical world we can touch with instruments, fly through, taste layer by layer. Titan gives us that chance, by understanding how light filters through Titan's smog, how photochemistry sculpts its atmosphere, how organics accumulate on its surface. We sharpen our tools for reading the skies of distant planets. Titan becomes a Rosetta Stone for hazy worlds orbiting other suns. When we decode its atmosphere, we are not just unlocking Titan. We're learning how to recognize and perhaps one day identify life-bearing chemistry on worlds we may never visit. In doing so, Titan quietly rewrites our philosophy of what a habitable world can be. For centuries, we imagined habitability as a narrow band, a planet like Earth, at just the right distance from its star, with oceans of liquid water and a temperate climate. Titan breaks that picture open. It orbits far beyond the traditional habitable zone, yet may host liquid water within and a functioning liquid cycle on its surface. Its sky is too thick, its sunlight too dim, its temperatures too low by Earth standards, yet its chemistry is vibrant. Titan forces us to widen our gaze. Maybe life can thrive in buried oceans that never see a star. Maybe it can flicker into existence in methane lakes under a smog-choked sky. Maybe worlds we once dismissed as too cold, too dark, too strange are in fact laboratories where the universe tests different versions of alive. Standing on Titan, if we ever do, would be to stand inside a philosophical challenge. Every breath we couldn't take, every step in a pressure suit, would remind us how specifically Earth-tuned we are, and how narrow our intuition is about what counts as a real world. And this is where the terror and the wonder finally meet. The same atmosphere that smothers our descent protects delicate molecules from cosmic radiation. The same brutal cold that would freeze our flesh solid preserves complex organics for eons, slowing their decay so we can study them in detail. The same thick haze that blinds our landers shields a surface that may be conducting chemical experiments older than life on Earth. The physics that makes Titan hostile to us is precisely what makes it precious to science. Every risk we take to land there, every engineering nightmare we solve, surviving the pressure, the cold, the distance, the delay, is an investment in understanding our own origins and our place in a universe that may be far stranger and far more fertile than we dared to imagine. To descend into Titan's orange twilight is to accept that awe and fear are not opposites. They are partners. The terror reminds us how small we are. The science promises to show us how big life, in all its possible forms, might truly be. We have walked, step by step, into an alien nightmare. A world where the air itself weighs on you like a hidden ocean, where the atmosphere is so thick and heavy, it turns falling into slow motion. A world locked at minus 179 degrees Celsius, where cold is not a sensation, but a sentence, and water becomes harder than granite. Here, lakes and seas are not filled with water, but with liquid methane and ethane, chemicals that on Earth are fuel, but on Titan are the substance of waves, rain, and rivers. We have seen how landing here means surrendering sight as our primary guide. The orange haze swallows sunlight, erasing shadows and horizons. Descent becomes an act of faith in instruments and equations, not eyes. Radar and infrared replace instinct. Every meter downward is a calculation, a prediction, a hope that the alien surface below is where we think it is, and not hiding cliffs, dunes, or liquid that could swallow a lander whole. Around Titan, even time behaves differently for us. Radio signals crawl across the void, taking more than an hour for a single round trip. No real-time corrections, no quick fixes. When a lander falls through that smog, it falls alone. Every decision is pre-programmed, every contingency imagined months or years in advance. By the time we receive the first image, the drama of descent is already over. Success or failure has been sealed in silence, and yet we have done it. Huygens cut through Titan's atmosphere and lived to tell the tale. Parachutes deployed in the crushing air. Heat shields survived a world colder than liquid nitrogen. Instruments tasted an atmosphere that had never known human presence. Soon, Dragonfly will attempt something even more audacious, not just to land, but to fly across this frozen moon, hopping from site to site, through a sky denser than Earth's, powered by the very physics that make Titan so terrifying. This is the quiet miracle of engineering. Behind every heat shield, every parachute line, every line of code, there are people who looked at Titan's hostile equations and said, "We can work with this. We can turn crushing pressure into a cushion, frigid cold into a predictable constant, hazy skies into a navigational map. We can transform terror into trajectory." In doing so, we reveal something deeper about ourselves. Our willingness to face the terrifying physics of Titan is not just curiosity, it is a declaration of who we are as a species. We choose to go where we cannot breathe, where we cannot stand unprotected, where even light struggles to arrive, because those places hold answers about how worlds form, how atmospheres evolve, perhaps even how chemistry becomes biology in the deep, slow cold of alien seas. Every terrifying challenge we overcome on Titan teaches us two stories at once. One is about the universe, about methane rain and frozen crusts, about ancient organics and possible hidden oceans. The other is about us, about our patience, our precision, and our refusal to let fear draw the borders of our map. If you enjoyed this journey into Titan's physics and the strange beauty of its dangers, consider giving this video a like. It really helps more people find these kinds of deep dives. Let me know in the comments. Where in the world are you watching from? I love seeing this little community stretch across Earth while we talk about other worlds. If you'd like to go even further and support the channel directly, you can also join as a YouTube member. You'll be helping make more long-form explorations like this possible. But as always, that support is completely optional. Your time, your curiosity, and your presence here are already a gift. And if you'd like to keep traveling deeper into the solar system with me, through alien storms, frozen seas, and the strange edges of physics, don't forget to subscribe before you go. Because Titan is not the end of the story. It is a reminder that the most terrifying unknowns are not walls. They are doors waiting for us to step through.